Hello, Christian. How are you?
Doing well. How about yourself?
I'm doing very well. So I'm going to introduce you here. And correct me if I say this incorrectly. This is Christian Merrill. He is many things, but first and foremost, an AI researcher. I was doing that for many years. And he was in the U.S. Army for 4 years. And for even longer, he's been working at Bristol Myers Squibb,
Yep.
which, if you don't know, that company that's sort of under this famous umbrella called Big Pharma, and spent quite a few years there, and currently is the associate director of AI and data science. So, hope I got all that right.
Yeah. No, that's definitely the title I currently have.
Well, with that title being said, my first question is like, what do you feel like you do every day? What's it like to be Christian?
So so I actually so it's actually kind of fun, in my opinion. Part of the reason I've stuck around the same organization, bouncing around the company. A lot of my day to day is being able to solve interesting problems, right? And being able to look at what's currently going on in terms of like the open source community, and then being able to try to, bring that to bear, outside of just the confines of an academic paper. Um, and right now it's even more exciting because the community has kind of exploded. And right now it kind of feels like every day is like a good day in data science right now, or every day is like a good year, sorry, in like data science right now. It's just, there's hundreds of papers being published. The technology is rapidly changing, especially in the space that I work in, which is computational linguistics, or NLP. Um, but yeah, no, it's really, I think it's just exciting, right? It's like every day's Christmas. There's a new technology that I get to play with, or try to implement. And everyone seems to be very excited about doing it right now. Historically, the space hasn't moved very quickly, and so it's not been, the demand has never been like, hey, we need like 1,000 things done now. It's been, you know, you'd get lucky if people wanted to spend a lot of time with you.
So you sort of mentioned the space, computational linguistics. So I'd like to hook on that, just to give the audience an idea of, what it is. So could you just explain that really quickly, and then we can sort of use that as a basis for the rest of the conversation?
Yeah, sure. So computational linguistics is kind of like the formal name of the umbrella term that a lot of people call NLP, or natural language processing. So it could be anything from looking at how you can parse through natural language text to do something with it. It could be, building out algorithms to do things like sentiment analysis. It could be, some of the newer exciting things on building conversational agents, but it's more of just a giant blanket term for basically looking at natural language and then doing stuff with computers to work with it. Um, at least that's how I've been kind of defining it. As opposed to like NLP is a very like a narrower subtask inside of it. It's kind of like, like in machine learning, there's deep learning, and there's different types of like the supervised, unsupervised learning. Um, but it's just an umbrella term.
Got it. So how does NLP then fit into the computational linguistics? Like, how does it fit into that umbrella exactly?
So I mean, it's kind of synonymous nowadays, but NLP in itself typically is you're trying to do something with language in terms of like parsing it or doing some sort of processing with it. Um, but broadly speaking, you could be looking at a whole host of different things. Um, Everything from what types of like parsing out. A good example would be like parsing out earning call transcripts. Okay, this is a person's name, and identifying it as a name, and then this is a title, or this is content. Um, yeah, so it's all kind of synonymous nowadays. It's gotten a lot different than at the very beginning.
What are some of the cousins of NLP? So that are inside that umbrella. So if we were going to see some of the other spokes of the umbrella, what would you give?
Yeah, so you'll see like symbolic NLP. You'll see things like statistical NLP. Statistical NLP is a lot of what we were doing um, like prior to 2010. Um, so a lot of things like spacey, they'll use statistical models to then, do different tasks, whether that's trying to determine like the next best word, kind of like type ahead on your phone. And then nowadays we're kind of in like neural NLP, which is a little bit more with like the transformer models using deep learning. I believe it was originally like recurrent neural networks were the big thing originally, and then they kind of blended into LSTMs, and then now the transformer architecture seems to be the most prominent.
Isn't a transformer just like a higher order version of statistical NLP?
Yeah, but at the end of the day, yes, it is all again averaging across the probability distribution. Um, but the actual approach of what you're doing is going to be slightly different.
Okay. Okay. So moving sort of away. So I guess I want to tie this back to like what you do every day. So how does all this help you, at your job and what you do? Like how do you use that to bring out some value for your organization?
I mean, it depends on the different use cases, but and broadly speaking, with some of the things that have really kind of opened up in the past couple of years, being able to do things like abstractive summarization, being able to basically break down large amounts of text to then be able to serve to somebody, has been super helpful. That's one that's pretty good. Other things has been like building out ontologies. So being able to kind of understand, like what concepts are inside of different bits of text, and then how that all rolls up into the broader organization. It's also like super helpful with diseases. So when you're looking at like medical text, it's good to know that that someone who had a heart attack, that rolls up into a very specific subset of diseases. Obviously, it's a myocardial infarction, so it's death of heart tissue, or that you have a specific type of cancer, and being able to target, okay, that it is cancer, yes, and then it relates to these specific tissues, or these specific organs, and then being able to go and actually use that for either doing things like search, like semantically searching documentation, or being able to be a little bit more targeted in what you're doing with this just large amounts of unstructured data as things to text. There's some other types of use cases. So we've also, like one of the things that I've done out of, basically out of desperation recently was building a recommendation engine for myself. This was like a little project I did on a weekend just for myself, because I needed to be able to kind of get in control of all the academic papers that were being released. Historically, it was, it's a good problem, but historically I'd spend like a couple of hours a week, just reading, and that became impossible. And so building a recommendation engine that basically reads through these abstracts and papers for me, and then comes up with a recommendation of whether I should spend time there. Like these are the types of things that are very powerful in different organizations. Because I know that when we think of like pharma, a lot of people will look at things like, oh, you're doing like protein folding, or you're trying to design, drugs in silico, or there's a whole host of different types of use cases that people might associate. And there, folks do that, but that's not been the work that I've been doing.
Fair enough. Before you go into, because we could talk a little bit about I do want to talk about the research and some of the things that you're seeing that's interesting. I think that's going to be really exciting to hear about. But I wanted to talk about that a little bit later in the pod, because, well, why not? But I think at first I'd like to talk about some of the structures that you insinuated, like this idea of like when you're working with NLP, you have this bigger knowledge set that you're using as a filter for the value of a particular word. So with the way I interpreted, if you have a myocardial infarction I suppose you want to classify a heart attack in a report of a patient's well-being as a myocardial infarction. So you're sort of trying to get your machine to understand that this is in this category. But also based on the context of the writing. So the person isn't necessarily going to say that they have that, but the way that the doctor isn't going to say that they have that, but the way that they have written it, it has all the symptoms of of what could be classified on their myocardial infarction. So could you talk a little bit about that sort of those kinds of machines and sort of your experience building them?
Yeah. So I'm not actually like building like medical devices or anything like that. So one of the ways of kind of like looking at this from an intuition perspective is that words tend to mean, like with the company that they keep. And so when you look at like, let's say like a medical journal that's going to be talking about a specific type of disease, you'll tend to start from a pure statistics perspective, you'll start to hit, different types of term frequencies. And then that's kind of evolved now into, obviously the encoder only transformer model. So the big one that folks might be familiar with, BERT. And then obviously there's a lot more now. OpenAI has an ADA model that's made for embeddings. And then there's a whole host of, open source ones like MiniLM. And what these are able to do is to kind of help, instead of you having to maybe look at like term frequencies, what you're able to do is kind of encode the text into some n-dimensional feature. It's a vector at the end of the day. And then you can actually you can also encode like search queries like, heart attack or myocardial infarction. And then you can do things like cosine similarities or cross encoders in order to then try to like re-rank or to classify that, this piece of text is relating more, directly to this particular type of concept. It's very powerful in search. I believe that this is being done in a lot of places. You'll actually see this with a lot of the like OpenAI cookbooks for doing what's called RAG, or retrieval augmented generation. So you'll see that folks will set up like vector databases. I believe the OpenAI cookbook uses Pinecone. And what they'll do is they'll do some sort of a vectorization exercise with either, OpenAI's model or, some other model that's, freely available, or you could fine tune a model, right? You could take like an open source model and then fine tune it on a bunch of like, let's say in this case, we'll say medical corpora. So like a bunch of research papers maybe, or maybe you have like physician notes. It doesn't matter. Yeah, even a textbook, assuming that you have the appropriate licensing and everything to use that data, you could potentially use it to get, a more sophisticated embedding model for that particular purpose. You would embed that, and then you would put that into your vector database, and then you can do different types of like similarity lookups, and then that's what you'll see with like, hey, I want to ask questions of my documents, and so the OpenAI cookbook will tell you, okay, we'll put it into this database, and you'll use something like LangChain, or I think I've seen Llama Index as another open source package that's available
with the same sort of structure as or same sort of architectural intent as LangChain.
So it's a little bit, LangChain has a whole host of different types of features that it proposed. Llama Index, I believe, is more geared towards like the actual semantic lookups or search related use cases. I don't use either of them a lot right now, simply because I found that the packages are a little bit volatile. They're very rapidly changing. It's volatile in a good way, right? There's a lot of interest. The community is moving very fast, but I've had situations, internally where we'll try to use something like LangChain, and then they might change like a method call, or something will get deprecated and we didn't recognize that it got deprecated, and then it may cause issues. So I haven't used a lot of that. I've primarily been using LangChain for their recursive text splitter, which is like really, really great. it's been a huge time saver, where it'll actually split out, sections of text, but with some level of overlap, you can encode that. And then when you do your recall, you'll get those sections of text. You can kind of reconstruct things together and then pass that to your GPT-4 or whatever to give you like a summary or to, provide you a recommendation or, whatever you want to do, right?
It's recursive in the sense that the text that's associated with each other is smaller and smaller as you go deeper and deeper down the tree. Is that how I'm trying to visualize it? But is that what? Okay, go ahead.
So I think it's primarily a relatively naive text splitting algorithm. And so what it's doing is you have like a specific chunk size that you want, and you want a specific amount of overlap, and then it's just sitting there and kind of breaking down let's say your 100-page document into, chunks of the size that you dictated.
But for each chunk, there's a little bit of overlap basically, and that's as simple as that. It's not.
Yeah, I don't think it's. I mean, I'm sure you could get very creative, and we have in certain instances. We've looked at, doing full-blown like document layout and then trying to associate sections of documents, because then, hey, this section was the introduction or the abstract, and this one was like the methods. And then from there you can have, a better enrichment of metadata. And so you can say like, oh, well, I know that I only am interested in my abstracts, or I'm only interested in my methodology. And so I only want to search on the methodology. Obviously, that's going to be a little bit more performant than trying to, look across, every bit of the document. And so that it kind of gets into like, what do you want to do? And this again, this is a huge space, right? There's a lot that one can do inside of this particular space. But the recursive splitter, just kind of helps you split it apart, because a lot of the models will have a token limit, including the embedding models, right? So I'm sure you're familiar with you can only talk to ChatGPT for so long before it kind of starts forgetting things. And that has to do with you have a context window. And so, a token is basically like a portion of a word, or it could be a full word, or it could be, punctuation. And so you'll get let's say 4,000 odd some, tokens that you can fit into the model before the model has issues, or you need to get creative. With some of the open source models, if you go too big, you might run into indexing errors, or the generative model will just start spewing absolute gibberish. And then with some of the it's more than hallucinating. It's like absolute gibberish. Yeah, it's worse. But that's only if you go beyond it. OpenAI's APIs, as well as any commercial service, will probably stop you. They'll give you an error.
Yeah, it just is. I think it just gives an error at these points, I think.
Right. And a lot of the reason that you split this stuff up is so that you can get that, those segments, and put more relevant stuff into your model so that it's able to do something. On the embedding side, what ends up happening is typically it'll be you'll get an indexing error. And so things that you can do to kind of get around it is to truncate, by your max length. So let's say you have 512, let's say just words or tokens, and you truncate by that. Or what you can do is you can split it up into those segments and then do some sort of an averaging technique. The downside to that is that typically if you
some data loss.
Yeah. Do you get data loss or dilution, right? So you won't get as high of a quality of the semantic search. Yeah. And so there's a lot of engineering challenges to all of this. I wouldn't say that I'm sure that there's solutions that are out of the box where you can kind of feed stuff in, it'll do a lot of this for you. But I'm not 100% certain what the best approach is for, if I could give you one approach, this is the approach that everyone should be doing. I don't think I have that.
It seems like, there's it is very, it's a very powerful tool, but its power is almost creates an illusion of a bigger boundary than it has. Like even just what you spoke about now, something like summarizing a whole, let's say maybe a book, right? Since there's a 4,000 token limit, you just can't really do that. You can only summarize a chapter at a time. And then you can sort of cheat by just like summarize all these chapters and summarize the summaries, which is what you talked about. But you have a dilution issue where you can very quickly lose. You don't have any control over the kind of context you're going to lose, or you have a tough time controlling that context. And then by the time you fix that up, then you may as well read the book. So,
Well, I don't know if you necessarily need to, not try to go and, well, so there's definitely approaches, right? So there's been a whole lot of research into this. Some of it is, hey, maybe I'm going to have it take notes. So maybe I can fit like a chapter at a time. And so I'll have it take notes of each of the different chapters, and then I'll pass that into my, I'll compile that together and then I'll pass that in, right? You have control of the context. And then you might have, there's other things that I've seen, beyond just like note taking or storing it. There's a lot of research right now on how can we increase the token lengths. I know that there was a model, it's called MPT. I have to double check what the token length was, but they trained a 7 billion parameter model to have this like absolutely absurd context length of 65,000 tokens. This absolutely absurd token length. And what they did, I think, is one of their tech demos, is I think that they put like the entire Great Gatsby into it. And then they had it write an epilogue for them. And it did well. But yeah, there's definitely a lot of research into this problem.
What were they using to make this work? I'm assuming they just pour more power into the problem. So they did that was the answer? Just throw more CPUs at it?
It's twofold, right? So historically, the reason that like token lengths have been short has been because you would need an exponential amount of compute power in order to continue to extend it. We've gotten around that using different types of attention mechanisms or making them more efficient, and so it's gotten a little bit more to a linear relationship. And with the case of the MPT one, I believe that they just did throw 8100 at the problem. It's a 7 billion parameter model, so it's a little bit on the smaller side. In terms of, you've got Llama 2 at 70 billion. I think OpenAI is 100 and something. GPT-4 is supposed to be, I think, like a set of 220 billion parameter models, although they don't really release a lot of this, so you don't exactly know for sure. But yeah, they took a smaller model, and they basically threw a lot of compute at it. And it's the same with even, like Llama. I think Llama out of the box is 2048 tokens. I think the original Llama was. And I believe, I have to double check. I can just check for you real quick. But Llama 2, I believe, is 4,000 tokens. Yeah. So, and people have already started extending it. I know that there's a Long Llama project where they've extended it to a larger number of tokens. So there's a lot of work being done. And in terms of the compute piece, there are some things that we can do to kind of make things a little bit more tolerable, right? So when we think about large language models, typically, or at least historically, they were in like floating point 32-bit. The weights were, and they're huge, right? So if you can get, 70 gig, 100 and some odd gig binaries of just the model weight. And so one of the things that has been kind of trending recently, which is super exciting, and something that I've been following a lot, is this idea of quantization. So what we found is that you can actually reduce the precision of the weights and continue to get really good performance. Yeah, I won't say exactly the same, but you can not get a specific, like, significant degradation of the behavior of the model.
Okay, so there's an order of magnitude reduction in the amount of precision every bit, it's basically every place value that you remove, right? So how are you still maintaining accuracy even though you've lost that, or how you still maintain the result? Accuracy might be the wrong word. How you still maintain the result with that level of loss?
So that's a great question. Yeah, that's a great question, and it's one that I'm not. I'm not entirely certain why one can get away with dragging it all the way down to 4-bit and still getting, really good performance. It seems that 4-bit is kind of the minimum. There was a paper that explored this called SPQR, and they released a package called QLoRa. And so that paper particularly, what it discusses is like, okay, how low can you go? Like, what's the bottom? And so they started just reducing the precision of the weights. I believe they started at 32-bit precision, and then they went down like below 4, and they found that around 3-bit precision, it started to start having issues.
Yeah, but that's a lot, though. That's a big jump. 3 from 4 from that number to 3 is a lot.
Yeah, it's got really, it's very good for, folks like myself who want to, at home do my own, research, as well as, even large enterprises, and it's even probably good for Google and OpenAI and Microsoft, right, or Amazon, whoever, right? Because you can fit a 13 billion or 16 billion parameter model on like a single A10 GPU instead of needing like 4, or having a large set of A100s to do something. Now there are some downsides, right? One is that you have to have a relatively modern GPU. If you try to use like some of the old what would be like the K40s or K80s, or the model that would have been below the 30 series, or so they aren't as efficient, because they can't support the matrix multiplication out of the box. And when yeah and when they first did the 4-bit, like I remember when Bits and Bytes first released their 4-bit implementation, like you could train the 4-bit model, and it would train really, like you could do a fine-tuning exercise using LoRa, which is low-ranking adapters. You basically put weights on top of specific modules in your model, and then you train those instead of trying to train the entire model. And so we were doing it with 4-bit, and it would go really well. And then you try to do inference with 4-bit, and it would take like 50% more time just to spit out the same answer, which, obviously that's not very good. But they recently released, CUDA, like a CUDA kernel, to fix this particular problem. And now it's very fast. It's just as fast as 8-bit or 16-bit.
So it sounds like, and this might be fundamentally wrong, but if it takes more time, but it trains the same, right? That's what you're saying. It changes the same speed, but it takes more time to get the result out. That the models, it just needs more, that the fundamental thing that does the prediction doesn't really need, how do I put this? It needs more space to make the prediction itself, to generate the reality that it spits the value out with. But the reality itself has a minimum size.
Yeah, so I think I understand what you're saying. So you're saying that the weights themselves have some level of minimum viability, and that they have to be at least a certain size in order to be able to execute the way that we're expecting them to execute.
Right. But specifically, like, the rest of the space isn't really for the model itself. It's just for it to generate. It's just extra space for it to make a prediction or something. Prediction might be the wrong thing. Space might be the wrong word. Something else. But it's like, it just basically, it's almost like you need a big table to make a big breakfast, but you can make it on a small table, right? But it's just going to take more time.
Yeah, a lot of that. So what's interesting is a lot of the slowness just is, at least originally, was just because of you were basically putting like you're basically trying to do something in software instead of on hardware, or you were trying to like get around something. So you're basically multiplying your matrices in a very inefficient way. And so once they patched that, once they basically enabled native support on the actual GPU through whatever it was that they created, I believe it was like a CUDA kernel. It no longer, they weren't trying to use some like PyTorch abstraction to try to like influence this piece, and it's gotten a lot faster. It's actually almost as fast as like a 16-bit or even 32-bit. It's like ridiculously fast now. I say that go ahead.
So it's the same thing. It's just happening on a lower level, and that's what's giving you the speed. So that's really what the value was. Is that they just put it lower down the stack.
Yeah, I believe so. And it's basically just creating efficiencies where they can. Because Python's notorious for being slow. I don't think anyone would argue that Python's super fast in comparison to like C++.
Well, the only reason why we're using Python for anything that has to do with data science, because it's using C Python underneath, which is everyone knows that. You know what I mean?
Well, yeah, and it's a really nice language to work with. It's easy to write, and you're not putting semicolons at the end of every line, and yeah.
So sorry, we got so deep into this, I almost forgot we're recording. But let me go back a little bit to all the way back. One of the things I wanted you to explain was sort of with the different measures of distance in your vector when you're trying to grab data from vector databases, how they affect your results. So could you talk a little bit about cosine similarity and other ways of sort of using other concepts of distance and what kind of results you get when you use one or the other?
Yeah, so primarily the one that most people I think default to is cosine similarity. The other one that we've used, or at least that I've used, is L2 norm, which is Euclidean distance, if I can pronounce that right. And so, they're just ever so slightly different ways of trying to do some level of, I believe it's just a projection, right? It's a linear projection of your vector spaces because you have two different vectors. Honestly, I'm being like super honest, I haven't seen significant differences between the two methodologies. And maybe that's just because I like to use like a blended retrieval. So I don't just rely on a vector retrieval. I do both a vector retrieval and like a BM25 retrieval, which is like a more traditional keyword, term frequency, inverse document frequency, like retrieval. And I found that kind of helps balance out some of the noise that you might get with something like a vector lookup. And again, not all vector lookups are the same too, right? You have a couple of options. You could brute force it, right? You could go through your entire corpus and determine get a score and pull it back. But typically what I've been doing is like an approximate nearest neighbor. Because I really like there's a piece of open source software that was actually forked by Amazon called OpenSearch. And so I really have been enjoying using that particular product. And this obviously isn't sponsored by Amazon.
Jeff who?
But I've been enjoying that particular piece of software in order to do this because it's just very user friendly. And it allows for a lot of different customization. It also has, I believe, Hugging Face support now directly into it, so you can actually put your embedding model inside of the actual OpenSearch instance itself, as opposed to having to do it externally.
If you like what you saw, take a look at the description. You'll see segments. You'll see the full podcast. Go take a look. Please go listen. Don't forget to like and subscribe. Thank you for watching. We'll see you later.